Okay, let's begin. So we're looking at this diagram for one of Hugo Zucchini's Ferris wheel shots, and we should just be looking for all the information in this, so taking a moment to take it all in. Alright, so we notice that it's 5 meters off the ground where we shoot from, and we also land 5 meters off the ground, so that's telling us that the y displacement is going to be 0 overall. We're looking at this initial speed of 40 meters per second, but it's at an angle, so we know we're going to have to take components using that 50 degrees. And it better be the case that when we're 24 meters into the jump, we're above 20 meters in terms of our height, because if we don't, we won't clear that. I assume that's something we're going to have to find, and that's sort of all the information on that page. So when you look at the diagram, make sure you're sort of quickly going through that in your head, just thinking about what's the information being given by this diagram. Okay, so we're going to find the horizontal and vertical components, like we're asked to. So the horizontal component, ux, is going to be equal to the speed, 40 meters per second. That's going to be cos of the angle of 50 degrees, and uy is going to be the sine. Let's just check that we've got the angles right there and the speed. Yep, 40 meters per second and 50 degrees. Fantastic. I don't know cos of 50 off the top of my head, so let's get that out. We're going to say, okay, 50 take a cos times 40 meters per second is 25.7. Actually, let's just stick it right in here. 25.7 meters per second. 3 sig figs is probably enough there. I mean, people don't generally care about the centimeter per second, but you could put a 4 there, that would be fine as well. Rounding it off to 2 or going past 4, you're probably not really giving the amount of precision that somebody would ask for a speed. uy, on the other hand, is just going to be the same, but sine. And so that's going to be 30.6 meters per second. Okay, so that's question 1 done. That's 2 marks. You want that line there to show that you've done the right substitutions, but you don't actually have to put the extra line in. Okay, maximum height above the ground. So whenever we read maximum height, we should be thinking of that the vertical component of velocity is 0. So down the lighting situation, partially at least. Let's continue with that. So maximum height means vertical component of your velocity is 0. So we're just going to sort of stick that into some subats now. So let's do that. Let's look in the x direction. Well, what do we know? We know that the initial speed, the displacement, well, we don't really know that. So that's unknown. We have the initial velocity. We found that in the last part. That was 25.7 meters per second. V in the x direction, well, that's actually going to be unchanged. So that's going to be also going to be 25.7 meters per second to the minus 1. If you didn't see that straight away, that's actually fine. You won't end up needing that. But that will just happen to be true in this case, because the acceleration in the x direction, of course, is 0. That's what makes projectile motion. And then lastly, we have time, which we don't know, but we might be able to find that out. In the y direction, in the vertical direction, we have Sx equals, well, that's the thing we actually want. Let's call that h. Sometimes I signify that with like 3 question marks or something, or put a circle around it. Just remind yourself somehow that that's the thing you're actually aiming for in the end. We have the initial velocity in the y direction, and that's 30.6, not 20.6 meters per second. And this is where we use that fact that we're at the maximum height. If we're at the maximum height, then that means we're not going up, we're not going down, we're just going flat for that moment, which means Vy is 0. And A, of course, in the Vertical direction is negative 9.8 meters per second to the minus 2, as it always is in projectile motion. Now, notice that we've put a lot of information on here, but we don't really need all of it. We're just looking for this here, and we have this, this, and this. So we have three things. We can find the fourth. We don't even need this X direction stuff at all. I think it's usually a good idea to write it down, just so that you know that you know that you know everything. But we're not going to use it in this case. So we need to relate S, U, V, and A. And the one that does that is 2AS equals V squared minus U squared. Plug in the things we know. That's the H we're looking for. Of course, V is 0, and then U is 30.6 meters per second. And then we square it. Okay, so we're just going to solve that for H. And when we do that, we get H equals 47.9 meters high. Once again, if you went one extra sig fig or one less, you're probably fine there, as long as you showed how you got there. Yeah, so 47.9. Let's put it in the box. 47.9 meters. Okay, next question. Safety net's got to be placed really carefully. We've got to find that distance R. So looking at the diagram, what is R? That's the horizontal distance we've gone when the vertical displacement is 0. So we're going to plug in, so what is it? It's the vertical displacement is 0. So that's the fact that we're going to use. Let's grab, just so we don't have to type it all again. Probably can't do this in your test, but I'm going to cheat a little bit. So we're going to grab all that again. We're just going to pop all that information there. But what's changed? Okay, it's still the case that we don't know this, but this is actually the thing we want now. Yep, that's still true, the initial speed. That's still true that the final speed doesn't change in the X direction, although not something we need necessarily. That's still true that the acceleration is 0. We don't know the time. In the Y direction now, put the wrong subscript on there. In the Y direction, we now know that that's going to be 0, and that's the key fact if we're trying to find how far the thing has gone to return back to the same place. UY, that's not changed, that's just the initial speed. VY is not 0 anymore. Now sometimes people make the mistake of saying, okay, it's going to come to a stop because it's landed. VY is 0 once it's landed. That kind of makes sense, but that's not projectile motion while it's landing. So that VY we're talking about is the VY just before it lands, not once it's landed. So we don't know that. Right, A is though negative 9.8 and T is still unknown. Now, what we notice is, this is the classic problem where on this side of the equation, we actually only have 2 real pieces of information. Now you might think, oh, we've got 3, but this is really redundant given this. So, saying that these two speeds are the same is just the same as saying that we have an acceleration. So we really only have 2 pieces of information on the top there, but we want that third piece, so we're going to have to go out and find time somehow. The way we find time is we look in the Y direction. So, find time using Y direction, and the equation we're going to use is that one. Right, in this case, that means 0 equals 30.6 meters per second times t, which is unknown, plus a half negative 9.8. Don't forget that negative, because downward we're finding upward is positive. And that's times t squared. Right, now you notice that we've got a common factor of t there, so we can pull that out. So your basic math method stuff, 30.6 meters per second to the minus 1, minus 4.9 meters per second to the minus 2, t. Right. And so what we've got here is 2 solutions. We've got either t equals 0. That's not the solution we're looking for. That's when the displacement was 0 because it hadn't even been fired yet. we're looking for when the displacement is 0 because it's actually come back to the same height. So we're looking for that other solution, which is when this bracket here equals 0. So if we take that on the next line, we say all of that equals 0, and we solve, we're going to get t equals 30.6 divided by 4.9 seconds. Now, when I use that in the next bit, I'm not going to use 6.24 seconds. I'm going to use this full number here so that I don't lose anything in the rounding. But when we present it on the piece of paper, we just write that. So then we're going to use in the x direction to get r. And we're actually going to use that same equation, s equals ut plus a half at squared, but the a is 0. So it's really just s equals ut in the horizontal direction here. But in this case, so we're going to get r equals, so what's the initial speed in that direction? It's 25.7. 25.7 meters per second minus 1 times, what did we say above? 6.24. 6.24 seconds. And we get 160.49. 160.5 meters. Because I used that sort of a rounded off version of that speed there, I wouldn't want to say I knew what the fourth or the fifth decimal place was over here. So I'm just going to leave it there at sort of 4 sig figs just to really be more careful. We were being really careful. If we were being really technical, we'd probably go to 161 as well, and you'd still get the marks. And in fact, let's stick that in as our answer, 161. 3 sig figs is usually fine. Alright, question 2. We got Margot the Magnificent. She's trying out a simple design using a spring dug into the ground. She tests it using a mannequin that weighs 40 kilo. And we've got a diagram here. Alright, so let's just have a quick look. It looks like the spring would be 5 meters long, but they've compressed it downwards, and now it's only 2 meters long, so we've got a delta x of 3 meters. She's standing there, okay, the ground level's there. We're going to release the line, okay, yeah, so they're going to release the line, and that's going to throw her upwards. Alright. Suppose the spring is first compressed only by the weight of the mannequin itself. So that's not necessarily going to push it down that 3 meters there. And if it did, then it wouldn't be a very powerful launch because it would just sort of bounce off her way. So, oh yeah, that's only a compression of 11.25 centimeters. So much, much smaller. Right, so we're going to find the spring constant of that spring. Okay. So balanced equilibrium, that means the force that the spring is pushing up with, which is, remember, k delta x, is the same as the force that it's being pushed down with, which will be equivalent to the weight of the mannequin. So Fg on the mannequin there is going to be 40 kilo times 9.8 square seconds. And that is 392 newtons. And that's balanced by an upward force from the spring, Fs. So Fs better be equal to negative 392 newtons. Right? If we're saying gravity is positive here, we could define it the other way around. But we've got a force of 392, and it's going to be perfectly cancelled out by that force there. And that's going to be equal to negative k times delta x here is that 11.25. So 0.1125 meters. And then, of course, we solve for k. So it's 392 divided by 0.1125. And we get 3,484. 3,484. Let's stick in a decimal place, why not? Newtons per meter. Except if I do that, it's going to turn into a fraction. So units per meter. So what do we go? 3, 4. Let's go 3, 4, 8, 4. Probably enough precision. Nobody's going to care about the fifth sig fig there. And that's the answer to A. Alright, so now we push it all the way down to that 3 meters. And we want to find how much potential energy is stored in this region. Now, your temptation might be to say, okay, I'm going to find the force at 3 meters, and then I'm going to multiply that by 3 meters to get the work done, F times distance. But it's not fighting against that same force all the way. So instead, we have to look at how much work has been done in a different way. We're looking at sort of the area under a graph. But we actually have a formula for it, which is that the energy contained in the spring is equal to 1/2 times K times delta X squared. In this case, that's 1/2 times 3484 Newton meters to the -1 times delta X squared, so that's 9 square meters. And we get that the amount of energy contained in there is this times 1/2 times 9 equals 15,680 joules. There we go. Right, the latch is released and the dummy begins accelerating upwards. Draw a free body diagram representing the forces acting on the dummy during this time. Sensibly labeled forces. Okay, fair enough. Draw a word. Alright, let's draw some arrows. We know that gravity is going to be acting, so let's start with that. I suppose sensible is a relative term, but FG makes it pretty clear what that is. Been using FG all year. Okay, then we got to think about what other forces are going to be acting on that, and clearly it's the force of the spring on the dummy. Actually, because we're talking about the dummy, let's say this is FG on dummy, FGD. And then we're going to be able to talk about the spring with a similar format, and it will all make sense. Alright. Now, it's accelerating upwards, so that means it has a upwards net force on it, which means whatever vectors we draw upwards are going to have to add up to be something bigger than the vectors we draw downwards. Given that there's only one here, that means that force of the spring acting on the dummy is going to have to actually be bigger. Bigger gravity, sorry, and that's the force of the spring on the dummy. Now notice that both of the forces are on the dummy. Right? So that's every free body diagram we draw, it's always going to have forces that are all acting on the same object. Right? And if we want to accentuate this, let's make the dummy one significantly bigger than gravity. Done. And that's what you need for 2 marks. So 2 forces. So you got 1 mark there for labeling the correct forces, so spring on dummy and gravity on dummy. And you got 1 mark for the spring on dummy one being bigger than the gravity on dummy. Yeah. We're going to find the speed of the dummy as it's propelled out of the cannon, and we're going to assume that all of that energy that we found that was in the spring, so that 15,680 joules, all of that goes into the kinetic energy of the dummy. It's not quite true, because of course we also have to do 3 meters worth of work. We've got to get the dummy 3 meters higher in the Earth's gravitational field than it was before, but we're being told we're allowed to win all that. Just as a quick sanity check on that, that's 3 times 40, so MGH, so times 9.8. So we're missing about 1,000 joules by making that assumption. So it's not trivial, but it's not huge. So it's about, 1/15 of the correct answer we're going to get here. And in fact, if you did include that, I would give you the full marks for understanding that there was an assumption here that was going by that would significantly affect your results. Now remember, when you find the speed, you're taking a square root, so that 1/15th error gets even smaller, so you're not going to get a huge difference whether you do or don't take that into account. But the question says not to, so let's not. Right, so we're going to say that all of that spring energy that we had before, which was 15,680, all of that is going to get turned into kinetic energy. Right? And kinetic energy is, of course, half mv squared, fucking fine squared. There we go. We know that's 40 kilo, so it's pretty trivial now to solve for v. V squared equals 15,680 divided by 40 kilo times 2 instead of divided by half. Get 784. It's going to be square meters, 6 minus 2, and then that's going to lead us to a V of, take the square root of that, 28 meters per second. Just to show you what it looks like if we do it the other way. So instead of having 15,680, we're going to have 15,680 minus 40 m times 9.8 g times h, 3 meters, because we get 3 meters upwards as we fire. So we end up with 14,504 instead. We then double that and divide by the mass. So times 2 divided by 40. 725 instead of 784, and then take the square root, and we get 26.9. So, alright. So I'm not going to take marks off if you got that correct answer rather than this approximate answer. Okay. This next question here asks you to evaluate some of the energy transfers here. So in the previous question, you assume that all the energy was passed into the dummy. We've already seen one place where that's not quite true. Some of it went into the gravitational field. The platform will still be oscillating upwards and downwards after a launch. So, you know, when you release a spring, it goes dunga 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 dung. But that dunga dunga dung means that it has some kinetic energy of its own, which means not all the energy went to the kinetic energy of the dummy. And so if we were really doing this for a real human cannonball, we better take into account all those sorts of things. Because if we don't, we're going to assume Margot is going faster than she actually is. We're going to say she's going to go further than she actually will, and then we're going to put the safety net in the wrong place. So we need to sort of make sure we sort of think of all the different things that might be wrong here. So one we've already mentioned, which is that some work is done against gravity before she even leaves the cannon. 3 meters worth. Okay, what are some other things that might happen? She might rub on the walls on her way out, suckering some friction. There's lots of different ways. There's lots of different suggestions that you guys would come up with. As long as it was reasonable and it was something that's going to lose energy, and you can talk about sensibly about the work done. That basically, if Margot or the dummy is doing some work on something, then they're not going to be going as fast as this. The other thing you might want to say is that the spring is not perfectly ideal. Real springs are not, which means they don't give back exactly the half K delta X squared that you put in. So that, remember, was how much potential energy we gave the spring. When we let it decompress, it doesn't necessarily give us that perfect amount back. It's not an ideal spring. But there's lots of different things that you could say there, and as long as you sort of explain them and explain how they would leave her with less energy than she might otherwise have, you're going to get the marks. Okay. So the next question is about that wobbling effect. So it says, in each oscillation, the platform reaches a maximum height of 5 meters. So as it's going back and forth, it gets to 5 meters, and that's the spring's natural length. So that means when the spring gets to its maximum height in that wobble, at this point here, it has no spring energy. It's at its natural length. Natural length means no spring energy. Right? And that's why on this graph here, the graph goes to 5 meters. It goes to 0 at 5 meters there, the energy. And a minimal 4.9. So that means the spring gets compressed down to 4.9, and that's when it has its minimum height, which means it has its maximum spring potential energy. Okay. The gravitational spring potential is plotted here. Okay, so you've got the spring, you've got the gravitational, and then the thing we actually get asked to do is to plot the total energy of the system. Okay, so the thing to realize is that as it's wobbling back and forth, at these two moments, right there, right at the top, and right there, right at the bottom, it has no kinetic energy because it's turning around. It was going up, it's about to go down. It was going down, it's about to go. Can't find the video there. It was going down, it's about to go up. At those two moments, we have no velocity, which means we have no kinetic energy. So one, we're expecting the kinetic energy to be 0 here and 0 here. But two, that means since the spring potential energy is something here, kinetic is 0 and gravitational is 0, that means the total energy is exactly there. Same at this end, there's no spring energy, there's no kinetic energy, which means the total energy is just the gravitational energy. Right, so we can pop in a line there. The total energy is just going to be that line there. Right? So, if it's the energy of the whole system, then its energy can't change over time. It can change form, it can go from gravitational to spring to kinetic, etc., but no energy is getting lost from the system. And then the kinetic energy, let me start by doing a few points that I'm going to line up. Right? We know that the kinetic energy is 0 here, and we know that it's 0 here. We also know that it's going to reach a maximum somewhere in the middle there. And in fact, it's going to be right in the middle. It's going to be at 495. Right? So it's going to be at a maximum here somewhere. We don't know exactly how high. We can actually just go point by point and subtract off the rest of the energy. Since whatever energy is not in spring form or gravitational form has to be in kinetic form, we can just subtract from this each of these values. But given that we don't have perfect values for everything, it's all going to be a bit of a guessing game anyway. If you just made some sort of a curve that peaks at 4.95 and is 0 at the ends here, I'm going to give you full marks. There we go. Something like that for kinetic energy, and you'll be fine. So kinetic energy in blue, full total energy in black. Total energy being a perfectly flat line is really important. The exact shape of the kinetic is not super important as long as it peaks in the middle. The 2 marks for that kinetic energy, by the way, one is for saying it's 0 at the ends, and one is for getting the sort of general shape of it. Alright, Dangerous Dan, he's got a mass of 70 kilo. He's trying to do this tethered cannonball jump. Seems dangerous because it's, he'd be experiencing big forces, but it does kind of make sure that he will actually hit the net. It doesn't matter how fast he gets launched. As long as he stays on that circular path, he'll definitely end up there. So that's good. Here's a 30-meter long rope on him. So that length there is 30 meters. And so it's every length here along there. Okay. If Dan follows a perfectly circular path, the acceleration will be directed. Well, if he's in circular motion, we don't need to read anything else. We know that the acceleration is always towards the center of the rope, towards the center of the motion. So pivot is, of course, a place where the motion is centered. So it doesn't matter what point we're talking about, it's towards the pivot of the rope. If he happens to be at that point C, yes, it'll be down in the direction of gravity, but it won't just be gravity. There'll also be some tension from that rope probably. And if there's not, then he's in a bit of trouble because that means he's starting to fall under the influence of gravity rather than in this circular motion path. So that's what it's going to be C. We're going to find the magnitude of acceleration. Alright, well, we're used to thinking not about acceleration, but about the net force in circular motion. We know that F net, if we're in circular motion, is mv squared over r. But we also know that in every situation, everywhere in the universe, F net is equal to ma. That's Newton's second law. So if we don't know the centripetal acceleration in a problem, it's pretty quickly derived as just divide both those sides by m and get v squared on r. And we're just going to sub in our numbers. I'd usually write the line, even though it's a really simple substitution there, I'd write it just so that in case you do something wrong, you still get the marks for having actually done the substitution. In general, in VCAA, you're not going to get marks just for writing a formula. You actually have to show that you know what A is, what B is, and what R is. And the way you show that is you actually pop in the right substitutions. That's where you get the mark for using the formula, and then there's also an answer mark down here. 26.13, 26.13, 26.1 is probably enough detail on that. 26.1 meters per second is that acceleration. Now notice that that's bigger than gravity. So when we're at the top there, you're still going at 28 meters per second, still got a radius of 30, the net centripetal acceleration needs to be 26. Gravity's providing 10 of it, but the tension in the rope is providing the rest. Right? So we're going to find the net force acting on Daredevil Dan. Well, net force we've just realised is just mass times acceleration. So it's just his mass times that. So 70 kilo times 26.13 meters per second times 2 equals 1829. There we go. And in what direction? Well, at point C, he's going to be there. The center of the circle is going to be there, so that direction is going to be down. I think I was pretty generous here, and if you just wrote towards the center of the circle, I think I gave you the marks. Alright, at the top of the arc, find the magnitude of the tension. Okay, I'll do that. At the top of the arc. Okay, so if we think about the forces that are acting, we know that we have a net force, F net, of 1829 newtons down. Right? And then we've got to think about what is that F net force made of? Well, it's made of F gravity down, and it's also made of a tension force down, and I can't think of any other forces. Right. So, given that they're all in the same direction, we can kind of drop the directions and just treat it as an algebra problem. If they were in different directions, then we'd have to sort of work out which ones are negative and which ones are positive, but they're all pointing in the same direction, so we can be pretty sloppy about it. We can replace Fg with Mg, so that's 70 kilo times 9.8 2 plus Ft, right? And then we can solve for Ft. T equals 1829 newtons minus 9.8, 1143. Alright, so this question here asks, before the launch, Dangerous Dan had no velocity, and the cannon had no velocity. So the total system had no momentum. After the collision, Dan's moving at 28 meters per second forwards, or sort of diagonally forwards, while the cannon is still stationary. So we might have to interrogate what we mean by still stationary there. This would seem to breach the law of conservation of momentum. So why would it appear to be? Well, it seems like we've generated some new momentum in the universe out of nowhere. We had 0, and now he has some, and the cannon still has 0, so the total amount is something rather than nothing. So we need to explain that. Now, I'm going to give you the explanation that I was actually looking for, and then there's another thing that I'll probably give marks to as well. So what I'm looking for here is that Dan has increased in momentum which means that the cannon must have gained some negative momentum. So that's just a restatement of conservation of momentum. That's more of a scene setting sentence. You don't necessarily need that, but you want to sort of show that you understand what exactly is the problem before you actually answer it. Right, so Dan's increased his momentum, so the cannon must have gained some negative momentum. The explanation for that is the cannon then passes this momentum to the Earth. Right, so the cannon is connected to the Earth, or is touching the Earth, is in contact with the Earth. You could think of it as having a subsequent collision with the Earth, right? So it is the Earth which has gained this negative momentum, but because of its enormous mass, we do not see any change in its velocity. Or you could say, because we are also attached to the Earth, we do not see any change in its velocity. Both of those are valid. If the whole Earth moves backwards a little bit and you're on the Earth, you're going to move backwards a little bit as well. So from your point of view, you're just going to see the Earth just sitting there as we move together, while the cannonball's the thing that actually moves with respect to you. Now, I got sort of lawyered into this a little bit. I'm actually going to give people marks if they said something slightly different, so that was what I was looking for. I wasn't originally going to give marks for this, but people have made a fairly compelling argument in some of their answers. So if you said the cannon is much, much heavier than the cannonball, then you can base your answer around that. Right, so if you said the cannon is much, much heavier than the cannonball, after the explosion, the cannon does have some negative momentum, but its velocity is very small because of its large mass. From our point of view, it appears to be stationary or quickly, and then some people also said, or it quickly comes to a stop due to friction, which is actually kind of a backdoor way of saying that it passes that momentum onto the Earth, which was the answer I was actually looking for in the first place. But more talking about from the cannon, from the weight of the cannon point of view, rather than the fact that it's secured to the ground point of view. And I suppose you could imagine that this cannon is not actually secured to the ground. In a circus performance or whatever, it's probably not. It's rolled out on wheels, most likely, and then maybe some brakes go down or something. So there is a bit of ambiguity there, so I did allow people to say it's a really heavy cannon, and that's why it doesn't seem to move. So either of those would be fine. Alright, final question. Dangerous Dan lands on safety net to thunderous applause. The two photos below show Dan in his safety net. The left photo, he's mid-landing. He's being decelerated by the net. That's going to be important. In the second photo, the landing is finished and he's lying still in the net. So in this one here, he's just lying there, completely still. We want to draw the force from the safety net onto Dan. So that's going to be FND. And then we're also going to draw a reaction force to that. So if we're using FND as our symbol for that force, then the reaction force is going to be FDN. Okay. First off, let's just do Dan's lying still, because we're pretty familiar with how to draw forces on objects that are just lying still. So we know that gravity's pulling him down, and we know that the thing that's pulling him upwards is, pushing him upwards, is that force from the safety net. So we're going to label that one F net on Dan. Right, and that one's, it's got to be pointing directly upwards because we know it's cancelling out gravity. So So there's that one. Now we don't draw gravity on. We can't draw gravity on because that is not the force that we've been asked to draw. Right, we also need to draw the reaction force. Now the reaction force to an upward force is not necessarily gravity. And it is in fact almost never gravity. The reaction force to gravity is you pulling upwards on the earth. And that's a force that we almost never actually see or put into our calculations. The reaction force to a force of safety net onto Dan must always be, by definition, the force of Dan onto net. So let's just turn that arrow around. It's going to be equally sized and opposite. There we go. Let's also grab a label and put that on it. Now it's not going to be FND, it's going to be FDN. Okay. So, now, the strength of that, we haven't been asked to put it on there, but the strength of those two forces there is going to be the same as the weight force of Dan, because there's only two forces acting on Dan. There's this upwards force and this gravity. Right. Let's go to this one here where he's actually being decelerated. So he's still moving into the net at this point, and the net is slowing him down. Right. And it's important that we read that bit there. It's being decelerated by the net. So he was moving in this direction, and he's actually slowing down. Now that means that the force of the net on Dan now has to be stronger than gravity. If it was weaker than gravity, he'd still be accelerating downwards. But we're being told that he's actually being decelerated. So that means this force here that you draw must be longer than the force that you drew over on this side. It's got to be bigger. I also accepted if you pointed it in a different direction. Because he looks like he's coming in that way, you probably want to say that he's actually being pushed to the left a little bit to take away some of that rightward momentum. But I was pretty easy on that one. As long as you didn't have the arrow pointing sort of out to the right or something, then anything sort of either upwards or leftish upwards was okay. But yeah, I think if we'd been completely technical about it, it would be there. And once again, that's labelled net on Dan. And once again, we have a reaction force. Now, we might sort of, if we're thinking about gravity being a reaction force, then we just have it sort of pointing downwards like that. But we actually know that the reaction force has to be equal and it has to be opposite to the original force. So we've got to draw it the same length and pointing 180 degrees in the opposite direction. So something like that. And once again, we're going to label that one. So if you had this one pointing straight up, then this one will point straight down as well. But the important thing is that this one needs to be longer than this one, and these reaction forces have to be the same length as their pairs. So the 4 marks there were for 1 mark for having forces drawn on there with the correct convention, so coming from the point of contact or close enough to the point of contact is reasonable. So not having it coming from, drawn over here, just having it where Dan's touching the net. I'm not sure if mine's actually going to get that mark. But 1 mark for using labels that make sense. So labels that are F, thing, onto thing. And just make it really clear what force is acting on what. 1 mark for showing this left-hand force being stronger than the right-hand one because it's doing a job of decelerating and of sort of beating gravity, whereas this job is just doing a job of balancing gravity. And then lastly, that your reaction forces are actually reaction forces. They're not gravity, and that they're pointing equal in strength and opposite direction to the original force. Okay. I hope you've done okay with that. We got our video done in about 50 minutes, so that's not too bad for a 45-minute test. So hopefully you've done okay, and if I haven't marked your test yet by the time you see it, probably mark it yourself like this. Okay, thanks guys, bye.